Hey, how's it going, everyone? It's been a very long time since my last stream. In fact, I haven't even really looked, but I think it's been like, I don't know, 8, 9 months. Um, so, and I think last time I streamed, it had already been a long time before that, and I think I made the classic mistake of saying, "Hey, I'm back," and then I wasn't back. In my defense, though, a lot of things have happened. So some good, some bad. But let's not focus on the negative. So the good news is that I actually got a new job, and I posted about it on my Twitter at the time. I got a job at Google, which has been pretty awesome, I have to say. I'm working on the Google Chrome team, on the GPU team actually. It's pretty awesome. I'm learning tons of stuff. I'm not particularly a graphics expert, but I'm learning a lot about graphics, a lot about Vulkan. And what's really cool is that everything I do there is open source, so people can actually see exactly what I'm doing by just looking me up, which is pretty nice. So that's been kind of a big deal. And I stopped streaming last, 9 months ago or something, around the time I was starting to get ready to go work there. And when you start a new job, especially a job like this, it can be quite a task. And so I needed to cool down the streaming and focus on that. So that's one of the reasons. There are other reasons, but there's no need to get into that. But yeah, I've been thinking about coming back to this. I haven't, not touched Vectrexy at all. I have done some work on it, which I'll share a little bit of that, here on stream. But I was sort of looking for something more interesting to work on to get back on it. And I do have something that I want to work on. So I thought this would be a good way to get back in. So, yeah. So what did I want to say? So basically, Vectrexy has gone through a few transformations, but mainly it's the same thing. But some of the work I've done since the last time I streamed that I think are maybe interesting to point out. Let me see here. So you can see like there's steady progression through the time here. So it's not like I've done nothing. I wish I had checked where I was, but a lot of it I remember had to do with refactoring. I basically started splitting up my project into multiple CMake files. What I did, because I had basically one folder with everything in it. So now I broke it all up into multiple folders. Each one of these builds into a lib, except for one of them, which is Vectrexy, which builds into an executable. So I've got like a core lib, a debugger lib, emulator, engine. I have something called a null engine, which is something I can build and run when I basically want to have no engine. And this basically just runs the emulator, executes instructions, but there is no visuals, no audio, no input, because that's what the engine is in this case. It's the thing that sets up the screen and reads inputs and all that, and feeds all of that to the emulator. And the emulator is like completely agnostic to the platform on which it sits. So, and then you can see here. So actually, sorry, yeah, there's SDL engine and null engine, and then I think engine is above emulator, and it's sort of like the kind of utilities and stuff for the emulator to look at. It's like kind of engine aware, but not specific engine. And then you have the null engine and the SDL engine, and those are implementations. And then Vectrexy itself, which is really just a single main file that kind of ties everything together, and it builds into an executable. So that was really nice because it sort of allowed me to very clearly delineate the dependencies. So there is now a clear dependency graph here, and there's no more like symbols that are kind of, there's no like backwards dependencies. Everything is in one direction, and I had to clean up a lot of code for that to happen. So it was a very interesting exercise. Apart from that, I did a little bit of work on input. Yeah, I think it was over here, gamepad and stuff. Basically wanting it to be possible to configure input because it wasn't. So I guess I could sort of show that. Let me see here. How's this configured again? No, that's not what I wanted. Let me change this. I also switched to using VS 2019, so that's relatively new. All right, so here's good old Vectrexy with Mindstorm. I think the frame rate is being affected by my stream here, but it looks okay. So what I worked on is, if you go into configure here, so basically settings, there's a few things I did. You can change the system so that, like, the normal is when you reboot, it does this whole intro thing, which is kind of long and slow. There's a fast one that sort of gets right to the title screen, and then there's a skip, which the skip one just gets right into the game, which is really helpful. I actually took these bias ROMs from someone else who put it in his emulator. I asked him for permission, and he was gracious enough to give it to me. But yeah, so basically there's this configure button here for your input, and right now it's not very complicated. Player 1 and player 2, you can pick their device. If you pick, let's say, keyboard here, and you can set up the player 1 keyboard, and it basically waits for you to press inputs. You can say reset all to default, or you can push whatever you want. You also can choose the gamepad. I think I haven't done this part yet. You see, I have the button for setting up the gamepad, but it's not yet configurable. So that's it for input. So that was kind of interesting. And yeah, okay. So then the next thing is probably the most interesting thing I've worked on. So I decided to take a crack at making a Vectrex game myself. So seeing what that would be like. Because, I made an emulator, and it can play games, and that's cool. But I was like, what about making games? And at first I thought, do I really want to try and write a game in assembly? And the truth is, I wasn't actually that interested in that. So instead, I saw that there were people who were able to write games for Vectrex in C. So like if I bring here, you say, let's say Vectrex programming tutorial, and you'll find stuff like, what was one that I'd seen? I guess this one here. So no, actually, so this one here is going to show you how to do it in assembly programming. So I guess I'll write C, let's say, or GCC. And yeah, so then I found this here, and there's a whole bunch, but basically all the tutorials online show you how to set up this fork of the GCC compiler called GCC 6809. 6809, of course, being the chip for the CPU for the Vectrex. So someone made a fork and added the 6809 CPU as a backend. It is a fork of 4.3.4, which is a pretty old GCC, unfortunately. But that's okay. The only downside to that is that it's, anyway, I'll get into that. So basically, you've got this GCC, and this guy goes through a tutorial, and he shows you how to set things up. He provided a make file, but you can see that all the programs here are C. It's good old C. And that's fine, but I'm a C++ programmer, really like C++, and I thought, is it possible to do C++? And the answer was almost. Oh, I should see this one here. So this guy actually had started adding support for GCC 6809, but it turns out that this was not enough. I tried using this kind of thing, and there were problems with it. And in the end, it's been a little while, but yeah, I had to do some changes, not to GCC itself, because GCC totally supported building for C++ programs. The problem was the make files. There was some linker script problems. I had to write a little bit of assembly for the CRT so that when it like launches the game or launches the program, it will do things like run constructors for statically initialized objects. So if you have like a C++ class and you create a global or static object, before main even gets entered, we need to construct those. Those are things that just weren't implemented at all. And that's the kind of stuff that, it really showed that that no one had written any C++ for Vectrex. So I took on the task of getting all that stuff to work, and it did. And so what I have here is my repo for Vectrex Pong, and actually probably look better to see it on GitHub. Let's see here. So here you go. So if you want to check it out, just go to my GitHub, Vectrex Pong. You could take a look at this, and it's like I say here, it's a simple Pong clone. It's nothing, it's not really worth playing or anything, but it was more of an experiment for me to kind of look into it. In doing this, I learned a lot. Like I was saying, I had to come up with stuff like, I guess the interesting bit for that would be, where is it again? I think it's in, no, make. Yeah, it's in here. So yeah, this is the file that I had to modify. Fix CRT to correctly invoke C++ global static init. So I had to do like a little bit of code to get like the constructor table and start iterating through it and calling what they call initializer functions, which are basically constructors. So yeah, so I did that, and another thing that I did that was interesting was that in order to start using this was a bit of a chore for people. You had to have Linux, or you could use Cygwin, but it was extremely slow and annoying. You had to like install all these packages, download the thing, and build it. It would take a really long time, and it was just typical get set up for building on Linux. So what I did was I learned me some Docker. I didn't know much about Docker, but I learned how to create a Docker image, because I sort of knew about it, and I was like, hey, what if I create a Docker image for this? And that's exactly what I did. So you see, if you go to, where did I put it? No, not that. I think my Docker stuff is on here. Here it is. So this is GCC 6809 Docker. And it's really, really simple. It just sets up a Docker file with like all the steps that's needed to build, clone and build GCC 6809. So it installs all the required tooling, downloads it, clones it, builds it, and then it actually uploads it, or I uploaded it to Docker Hub. And so now all you need when you want to build, it's so simple. All you do is install Docker, and you do a Docker pull of GCC 69, or you don't actually have to do this because it's going to do it for you. You clone this repo, and you do Docker run, and you basically say, did you want to run this, excuse me, what did I do here? pwd, so current directory, root Vectrex Pong, and this is where you specify the image and the command that you want to run. So it's going to run, you're going to run make in it, and you're going to say which directory you want to run in. So with that, you basically can build everything. And so once I had that going, I decided to set up my VS Code to make it even easier for me. So this is VS Code with Vectrex Pong open. So this is all the source code. See, it's not many files, but I've started to build a library and stuff like that. And what I did was, in VS Code, you can set up these tasks. So I set up a bunch of tasks, initially running directly in Linux. I was using WSL for this, but I sort of abandoned that because it's not amazing switching between WSL and non-WSL. And also, like I said, I wanted to use Docker. And actually, WSL and Docker don't really work super well together. So, so because of that, I went another direction and basically just added here some scripts to make with Docker, make clean, and launch Vectrexy. So the way that works is at any time I can bring this up and say run task and say do make with Docker. And at the bottom here, you'll see that it'll execute Docker run Vectrex Pong, blah, 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 and it'll go and make it. And at the end, it even shows some stats. That's something I added to the make file to kind of give me a sense for, you know, what is it looking like. And probably the most interesting stat here is how much RAM usage, because the Vectrex has very little RAM for programs. It's about 618 bytes exactly for you to use contiguously. It's pretty small. In fact, no, sorry, it's not 618 contiguously. It's, what is it again? It's data plus the BSS. So actually, they do end up contiguously. No, sorry. So it is a block, one block of 618 bytes. In there, you've got statically initialized data, and you've got like statically initialized writable data, so globals and statics that are not const, and then regular data, so just, you know, objects that you allocate on the heap or whatever. So those all end up in this piece of RAM, and so far my program already uses 109 bytes, which is about 17% of all the RAM available. So it's very, very small. But of course, that's the Vectrex. It's a tiny machine. One of the reasons why it's okay that it has so little RAM is because the Vectrex has its own bias, and you can take advantage of that. So you don't actually have to write routines and for everything. There's a bunch of BIOS routines that you know take care of a lot of the vector drawing and manipulations and playing music and sound. So you get to you don't have to do all of that. You don't have to worry about having all that in memory as well because it's already taken care of for you. Okay, so that's cool, right? So then you can build like this, and actually, I guess I should do a clean, just so that you can see what a real build looks like. So I'm just gonna clean here, and then I'm gonna run a build. So here's the make, just again give you a sense of, like, you can see that it's already done there. It compiles a whole bunch of files here. It's a bit hard to read, I think, but you'll see like it's building source joysticks.cpp, source base CPP, source bias, source main. So building a bunch of CPP files, and then doing some linking at the end, and ultimately producing Vectrex pong.vec with the stats at the end. After that, I can run the task called launch in Vectrexy. I think it's this one here. Yeah, that's the one. So we launch like this, and then this is the game. And actually, if we reset and put 2 players, you'll see that you can actually control the second player here with the keyboard. So yeah, super simplistic, but obviously the goal here was not to make the game initially. The goal was for me to sort of get DevTools set up, see if I can actually do this in C++. Okay, hold on just a second. Oh, never mind. Okay, so yeah, and let's just quit out of here. Just to give a quick overview of how the code is, it's really like C++. So you see, like, this looks like C, of course, but what's what's C++y in there? I mean, it's stuff like namespaces, right? I think I had, did I see a namespace before? Not in this file. Okay, here. So for example, the object class, right? If we go to that in object.h, we have a class. It's got a constructor. Yeah, you've got another class here, vector list. So, you know, clearly C++. Now, this is one of the caveats. Because this is GCC 4.3.6, it does not support C++ 11 and up. So this is all C++ 03. So that's a little bit sucky because, you know, I kind of got used to all the nice additions to C++. But, you know, I did program for a very long time in pre-C++ 11, and, you know, you do what you got to do. A couple of interesting things in here are that I have written some templates. So let's see, I think it's here. So there you go. There's a namespace here. There's a bunch of templates here. These are templates for printf. And of course, because I don't have C++ 11, I can't do variable arguments to templates. So I got to do the old trick of like having a bunch of overloads for the number of arguments I want to take. So not amazing, but you know, this is the kind of thing we had to do back in the day. And actually this printf stuff is super cool, and I'm going to talk about it at one point. So let's see, what else can I show you? So this basically, let's go quickly over the code because I think it's kind of neat. So you start off with a little initializer for the BIOS here. You show the select game screen. So that's that screen you see where you have a number of players and type of game and all that. So that's actually something built into the Vectrex. I didn't have to like, I didn't actually have to program that myself. Basically, if you go there, show select screen, you'll see that I'm effectively making a call to a BIOS function. So these are all the BIOS routines for the Vectrex. This is not my work. This is actually the work, I believe, of this guy, Joachim Larsen. So, you know, he put together this file and macros and stuff. And all of these basically map to the BIOS routines. There's a bunch of inline assembly here. I had to do some changes to this to make it work and link properly. But yeah, ultimately it's his work. So, and you'll see that select game is really just jumping to a BIOS routine at a specific address, setting up a couple, like setting up these arguments into certain registers and then jumping there. So, and actually I copied the documentation from the BIOS file. So then we do that. Then after that, I have a couple of declarations for how to draw the paddle, the cross, I call it, which is really the ball, the border itself. Here is like a buffer that describes the paddle hit sound. So that's like when the ball hits the paddle or the walls, actually. I have basically a bunch of objects for what you see on screen. So you have one for the first paddle and the second paddle, and you can see that I'm giving it the vertices it's going to use to draw it. Just wondering, is this actually working? If any of you are actually watching here, maybe you can just throw me a dummy chat. I just want to make sure that that I'll see chats from people, just in case, you know, because I've had this issue before where people try to chat with me and I can't see it. So yeah, so you've got the ball here and the border. So those are obviously what you see on screen. There's also a text object for the score, and basically there are two scores for player 1 and player 2. Don't remember why I put 9 here. This should probably be 3. I think I was just messing around. This is how many characters you need, like the maximum text length. So I think this should actually be 3. So yeah, and then basically a bit of initialization. So I set where the paddle 1 will start, paddle 2 will start, and the ball's initial position. I set up the border's position. I grab the joystick 1 and 2. So joystick basically represents the inputs. Set up some speeds, a list of objects and paddles here, and joysticks. Set up the score, initial score, and then I start my infinite loop. And every frame you got to call this wait frame. This is sort of the function you need to call to reset the beam back to the 0 location. You have to do that, otherwise on the real Vectrex you'll have drift. Also, this function does a little bit more than just the weight recalibration, which is what I was talking about. It also updates audio, it reads buttons and joysticks, values. It also sets the beam intensity. So a whole bunch of stuff you got to do once per frame. I sort of tucked it in that function in there. And then after that comes the game logic. So we start off by moving paddles based on player input, right? So, I go through the number of players, grab their joystick, and check if you're pressing down and you're not past the bottom of the screen, I move you down. Otherwise, if you're pressing up, we go up. If you're pressing down, you go down, and you clamp your location. Don't know why this. Oh, this is an and. Okay. So yeah, we move the ball by its current speed, and and then I do some collision detection here. So ball paddle collision. So grabbing the paddles. For each paddle, I just check if it collides with the ball, and I have a very simple collision check function over here, just checking edges. So each object right now just has a quad. I compute the quad for each object when I create it. Very simple bounding box type of thing. And using that, I just look for quad intersection. If it collides, I play a sound. I change the ball's direction. This little loop is to continuously move the ball until it no longer collides. And usually that just takes one extra call. But this is just to make sure you don't get that problem of, the ball, let's say, goes inside the paddle, and then you tell it to change direction. But then in the next frame, it says, oh, I'm colliding with the paddle, and then it changes direction again, and it basically starts oscillating inside the paddle. So what we do is we change its direction over here, and then we just do a little loop and say, while you're still colliding with the paddle, start moving in your new direction, and that gets the ball out of the paddle or out of the wall. We do the same thing with the wall. After that, I grab the ball speed here. If the ball hits top or bottom, bounce, and I play the sound again. Similar kind of deal. If the ball hits the side, someone wins a point. So here, if I detect if I hit the right side, then I increment player 1 score. If I hit the left side, I increment player 2 score. And I also print it, which is kind of fun. Well, that's the feature I wanted to talk about, because obviously there is no real printing. Apart from showing text on the screen. Hey, Moosey boy, how's it going? And now I know that chat works. It's been a long time, man. Did you just join in? I've been pretty good, actually. Been pretty good. I talked about this at the beginning of the stream, that it has been a long time, and the main reason I've not been on is that I started a new job about like 8-9 months ago. So you know how it is when you start a new job, keeps you really busy. So I had a lot to learn. I had to ramp up, become a contributor. So yeah, but it's pretty cool. I'm at Google now, working on Chrome on the GPU team. I wanted to say one thing about that, actually, that was kind of I think worth mentioning, is that my lead, he interviewed me and wanted me to work on his team, and I remember asking him, like, this is a graphics team, and like all the team members are really like GPU experts, and I'm like, I am such a noob when it comes to graphics. I've done a little bit of graphics work, a bit of shader stuff in my emulator, but like when I worked in video games for 15 years, but I was never a graphics programmer, and And what he told me was that actually what was really interesting to him wasn't any experience related to graphics. It was my experience writing emulators. And I thought that was kind of interesting. And I know why now, because I actually spent a lot of time working on the product I work on, which is it's basically originally an OpenGL driver, but now a Vulkan driver that targets the CPU. And it does this by doing JIT, by just-in-time compiling shaders and stuff. So I won't get into too much detail, but the point is that there's just a lot of JIT in there, and I spent a lot of time staring at assembly code and, like emulating in effect, right? So he said that was interesting, and I just thought that was kind of cool because, I never got into writing emulators for getting a job. I did it because it's super cool and fun and interesting, but it's kind of neat that it turned out to be sort of helpful for my career. So, I think a lot of people have stories like that where you start working on personal projects and you never know where it can take you. So just thought that was kind of fun and worth mentioning. So yeah, so just sort of to wrap it up here. So this printf thing is kind of cool. Oh, thanks, Moosey Boy. So yeah, I'm going to get to that really soon because I think it's probably one of the cool, interesting things you can do with an emulator. And then finally, over here, I set the score on screen in those text box for the scores, and I end the frame by drawing all the objects and those text boxes. And then we loop again, and that's it. Really, really simple, right? So if I run this again, now that you've seen me go through the code, you'll understand pretty much what you see on screen here. So, that's the border. These are the score text objects. These are the paddles. This little cross here is the ball. I'll pause it here. And then of course you press inputs. You can move your paddle up and down. Oh, and over here, so you see Vectrexy is running this, right? Like this is my emulator running the game. And you can see that in the output of my emulator, there's these printfs for the scores. So that's the cool thing I sort of wanted to share. It's really just right there mixed out in the output. So like, this is the debugger. You can step and look at your trace and all that. But yeah. So how does that work? So I guess I'll get into that because I think it's kind of neat. So basically, I wanted a way to do printf, right? And I didn't really want to write a full printf or use a full printf implementation because it would be probably expensive in cycles. In terms of like the cycle budget for the Vectrex is very, very small. You have like some 30,000 cycles per frame, which is really not a lot. And I just didn't want to pay that kind of cost. And I wanted to also be able to show like complex printf statements, not just very simple ones on screen. So I thought, the right thing to do here is to have my emulator talk to Vectrexy. Obviously, this would not work on real hardware. So this is completely a development thing and a dev thing, but that's fine. So how I did this is rather interesting. So what I did is if we go here to the Vectrex, into the emulator, and we look at the memory map. Was it not memory map? Oh yeah, it's like this, memory map. Okay, so this is basically the memory map for the Vectrex, right? It's 64K. The first 32K is for the cartridge ROM. And as I wrote here, it actually turns out that there's 48K that can be used. There's this unmapped area between, say, the 48K, the first 48K for the cartridge, and where RAM starts. So RAM starts at C800. Cartridge ends at just below C000. And in between those two, we have about 2K of completely unmapped, unused memory. After that, there's like a couple of shadow. There's some memory mapped registers to talk to the VIA. There's some memory you should not use, which we call illegal here because it basically maps both VIA and RAM. So we don't touch that. Oh, and then the last the last 8K here is split into two. You've got Mindstorm in the first, I forget what is it, the first half, so 2K. Yeah, so the first 2K of the last 8K. Oh wait, sorry. 4K. So the 4K here is for Mindstorm, and then we have another 4K here for the BIOS itself, right? Oh, all right, Moosey boy. Well, thanks for checking in and saying hi. Take care of yourself, man. Yeah. So anyway, the point is I was looking at this 2K over here and thinking, why don't I just use this unmapped region as, you know, my development memory mapped register region? And that's exactly what I went and did. So I have a developer memory device. So in my emulator, I have all these things that derive from iMemory bus, and these are all the things that are on the memory bus, and any request for a read or write goes through the memory device and goes through the bus, and then it looks for devices that are attached and cover a certain range of addresses. So I added this dev memory device. So like I say here, it replaces the unmapped memory device, exposing new memory mapped registers useful for Vectrex game development purposes, right? And what I do is I started, you know, reserving addresses in there to have very specific functions. So over here, you'll see that I use, I don't know, like 1, 2, 3, 4, 5, 6, 7 registers for printf. And I describe it here. So these are printf registers. So the first write each arg in left to right order by writing to one of the push registers. So you've got like push arg8, push arg16. So if you're going to push like, you know, something that fits in, that's just 1 byte or 2 bytes, you use one of these. Hey, saidwho12, how's it going? So yeah, so, you know, Vectrex doesn't have lots of data types to deal with, so it's kind of simple. We basically have only integral types, no floats. I'm doing well, thanks. So we have no floats. We have, you know, our basic data type is an int8 and an int16. So it's really simple. You know, obviously if I needed more, I would just add more, but it's really simple. After that, you write the format string to dev printf format. So that's this register here. So you can see, like for arg8, I just need 1 register. For arg16, you write to 2 registers. I could have done like 2 writes to the same one and I accumulated, but I just felt it was just simpler to write the whole value once to a pointer, and it just writes it to both registers, and I take that. So this makes it easier on the implementation of the game to be able to write to it. So I'll show you that after. So then you push your printf, which is a pointer, and a pointer will be 2 bytes, 16-bit. So you write your format string to there, and actually, I think this is, oh no, sorry. All right, this is push this, push that, and I have another push. This is pushing for const char star. So this is pushing a null terminated string. So sorry, that's the other thing, because that's a very common thing we have to do. And then finally, what do I do here? Then write the format string to dev printf. So the format string goes into this guy here, and then it knows to go ahead and output. So saidwho12, you're asking, what is this emulator for? So this is a Vectrex emulator. The Vectrex is a old game console from 1982 that is completely vector-based. It came with its own built-in 9-inch screen. Here, I'll show you. Whoops. I don't know if you've ever heard of it. Yeah, this is what it looks like. So I actually own one of these. I showed it once. I know, right? This is a super cool machine. Like, I'm so happy to have one. and I wrote an emulator for it. And you can see like it's black and white, and you basically put overlays on it like this. So each game is a cartridge that you stick on the side. You can sort of see a little bit of the cartridge over there. I don't know if there's like a... Yeah, you can see here there's a cartridge. And then you stick an overlay in the front, and that adds color. And what was cool about the overlays is that you could see they sort of use it as a HUD where they describe the buttons, and some of the overlays were better than others, actually being useful for the game. But yeah, so that's basically the Vectrex. Yeah, so if you stick around, you'll actually see my emulator run, and you'll see what it looks like when we play. So actually, I'm not new to Twitch. I was streaming like for quite a while. This is actually my episode 99 technically. So I've streamed 98 episodes and on Twitch, and they're all on my YouTube. They're archived there. But it has been a long time since I haven't streamed. I think it's been like 8-9 months or something. So maybe even 10 or something. I don't remember. It's been a while. So yeah. But I'm trying to get back. My idea is to try to stream hopefully twice a week like I used to do on Tuesdays and Thursdays. But you know, I can't make any promises. We're going to see how it goes, but I'm going to do my best. You might write an NES emulator. So that was the first emulator I wrote, and I highly recommend it. I don't know how comfortable you are with programming, but you know, if you haven't ever written an emulator, a lot of people suggest writing. Was it that not real machine that everybody writes emulators for, or what's it called again? I always forget. The good first emulator to write. Chip 8. Yeah, that's it. Exactly. So, you know, I didn't do that though. I did start with the NES. I will say it was not easy. It's a challenge. The good news about NES though is that there's a lot of information out there. So, you know, there's that NES Dev Wiki. So it's really, really great. Okay, so your friend wrote a Chip 8. So is this the friend that you're trying to write your NES emulator with? Yeah, so NES Dev is like, it's amazing. And you know, I wish that there were resources like that for other systems. There's certainly not that for the Vectrex. I had to do quite a lot of digging and figuring things out. But having written one emulator before, it was a lot easier to get into this one. So you want to make it for the Vita? Makes sense. That sounds like a good idea. Right. I think SDL is supported on a lot of platforms. So my emulator, it targets SDL as well. You can see here I have SDL engine. You know, lots of SDL code. So you can see here SDL, destroy window and stuff. Okay, so just to finish off here, basically what happens is, now I'm just going to, before I go into the details here, I'll switch back to my Pong game here. And the way I did printf is I basically made a bunch of templates for, you give it a format and then you give it an argument. And it's right now I support 1 to, I think, 5 arguments. If ever I need more, I'll just add more. It's I didn't mean to like stop you from chatting. You just go ahead, man. I'll answer you. Anyway, so yeah, so basically I have these templates, and what they do is, say for the one where you pass it a format string and just one argument here. So what I do is I have this little helper function for pushing arguments. So push arg a1, and this is just for like overloading based on type. So I specialize this template based on the type of argument you push. So if you're pushing a uint 8t or an int 8t or a char, in all cases, I will just write the value to that special memory mapped register that I was showing before that is for pushing an arg8, right? An 8-bit arg. And if you try to push a UN16T or an N16T, then I will simply assign it to this guy here. And you know, these guys, they're defined as like volatile pointers with a type. So that's why, you know, to make life simpler, I decided to use, you know, two registers, two 8-bit registers for, let's say, the 16 one, so that you can just address the first one with a 16T pointer, 2-byte pointer, and it'll just write the two values when you assign to it. So that makes it nice and easy. And these values, of course, map directly to the ones up here. See, C100 is C100 for the push arg8. C101 and 102, well, I just have to list the first address, but it's for those two. And 103 is here, and then 105, 106 is this one here. So there's the direct mapping. When you push a const char star, I will use this register to write it to. So we start with that, right? So if you look at all these different printf overloads for the different number of arguments, it's pretty straightforward. I'm just calling this function for the specific arguments, and based on the type, it's going to do the right thing. And then I finish off by writing the format string that you passed in to the dev printf format memory mapped register, right? And then it'll print. So the way that works is I have a, where is it again? Write, yeah. So every time there's a write into this memory region, I have this handle dev write function here. Oh, thanks, man. It's just experience, right? It's not smart. It's if you spend the time and you know, you write code and spend the 10,000 hours or whatever it is, you know, you'll figure it out. It's just I guess tenacity, right? Just stick with it. Don't give up, and you know, you can pretty much do anything. So okay, so handle dev write. When we call it, it will look at the address that you passed in. And if it's any one of those addresses, I'll handle it. Otherwise, I'll just return false. And for example, if you decided to do the dev printf push 8, what I actually do, and this is actually not it's not standard what I'm doing here. It's a little bit of you know, non-standard code, but it's fine. I'm sort of like, what I mean is, I'm trying to make use of the whole VA list mechanism that compilers provide, but that is platform specific, you know, or even compiler specific, I should say, how that is laid out in memory and how that works. But, you know, see, I even see here on Win64 as a question mark. So I have yet to try this on other targets. I'm really curious if it's going to work properly on Linux. I know it works in 32-bit and 64-bit Windows, so that's covered. But I might have to if-def this code for the different platforms. But for now, it's fine because I'm the only one using it. So basically what I have is I have this buffer of printf data, and in there I store the arguments, I store a little vector of strings, a whole bunch of stuff. And ultimately what I'm trying to do is I'm trying to take the value and I'm just sort of laying it out in memory in the way the VA list expects. So right here, like I have this arg index that's sort of my index of where I am in this buffer, and it's based on the size of the arguments you're passing in. And as I wrote here, even though I'm pushing a 1-byte object for, at least for Windows, for the MSVC, all integers actually take the full size T value. So if it's on 64-bit, it'll take, yes, I use vprintf. So like if you're writing a char, an int, a short, or whatever, that will take up in the VA list space 32 bits if it's 32 bits, or 64 bits if 64 bits. So it's a bit wasteful, but you know, that's what they do. So that's why I assign it to a size T here, and then I write to my current buffer, that value, and I increment my arg index by the size of v here. So it'll be like 4 bytes or 8 bytes. Yeah, so VA list is it's not defined how it works. You know, that's compiler specific. So you sort of have to like look at it. I looked at the way, you know, because it's all in headers and stuff. I just looked at how it works and I kind of figured it out. It's not too difficult. 16-bit is sort of similar, same kind of thing here because it's just like 8. I just had to correctly, so for 16-bit values, there are 2 writes that occur, right? So what I do is I sort of, the first one, I just store and remember the first byte that got written, and on the second one, I take the first byte, shift it left 8, and OR it with the second byte, and together I make my 16-bit value, my 2-byte value, and then I do the same thing I did up here. And then ultimately, strings is a bit more tricky. I won't get into that. And the printf formatting stuff is right here. So again, it's 2 bytes because it's a pointer to a buffer, right? So remember the first byte. When I get the second one, I have it here. That's the format string address. And then I have this read string function that will read the format string from memory, because this is all like in, you know, Vectrex memory, right? In the ROM space. So I got to go and read it. So I basically do a little loop here and I read each byte. I get my string, my format string here, which comes back as a std string. And I do vprintf with that format string. And then I reinterpret cast my data buffer here to a VA list. So this is the part that's like very much, especially here, very much not, you know, it's not standards compliant. Doesn't C++ have another thing to do VA args? So C++ does not use printf, right? C++ offers the IOStreams library with cout and cin and all that crap. Cout and cin are, especially cout there, it's very, very slow. It's annoying to use. It's difficult to set formats for, like setting precision and all that. It's pretty crap. It's difficult to use. It's overly verbose and it's slow. Although I will say that I did consider doing something like cout, because actually it would have made my life a little bit easier. I wouldn't have had to do this kind of VA list buffer stuff. I could have just, you know, for everything that you want to see out, every time you pass like an object to output, it would just write the value to a memory mapped register, and I could have immediately written it to the output. You know, there would have been no, say, formatting to do. But then I did want to be able to format it and stuff, so you can use linked lists. Well, the thing is, I didn't want to write my own parser for formatting. You know what I mean? And so this was really the cheapest thing. It's not, storing the arguments is not the hard part, actually. The hard part is like the actual formatting, respecting the format and the format string. That's the hard part. You know, I could write my own, you know, it is pretty limited. I could say, you know, parse a string and look for the % and all that. But why would I? You know, vprintf does the right thing. So if I can just tell it, here's the format string, and give it the data, the pointer to the data that it expects it to be in with the right layout, it just does it for me. So it, you know, totally works, right? And then I flush it. And so if we go back here, let's say to main. So here's my Vectrexy printf call, right? Have you ever written straight C for a long time? When I started my career many ages ago, I did some C, but I've mainly been a C++ programmer. So, you know, I did some C because I was forced to. I was working on this embedded system early in my career, and it only had a C compiler, so I had to write C. But yeah. So yeah, I think it would be actually kind of neat just to show like how this works here. So if I set a breakpoint just on this here, and you know, I'll launch. Let's go here. So I'll launch Vectrex Pong here. I made templates in C. I made constructor also, multiple constructors. Did you know that's possible? I'm not sure I understand what you mean when you say that. Like templates, like you're sort of emulating templates the way, like you did something similar to templates in C++. Okay, so I just hit a breakpoint here. What I wanted to do was go into my debugger here and write set break into debugger to true. Okay, so where are we right now? Okay. So actually, you know what would really help is if I can load symbols for this. Let me do something here. I've been working on my laptop for this, so I'm not completely set up. Let me just get myself set up here. So if I go into Vectrexy data dev debugger startup. So I'm loading symbols. I always load symbols for the BIOS, but let's also load symbols for, where is this here? Yeah, I support, yeah, it's here, this map file. So when I build Vectrex Pong with GCC, it generates a whole bunch of files here. One of them is this map file. So the map is basically giving you all the symbols and their addresses. Unfortunately, they've got the C++ name mangling thing going on. I can do like a little demangling at one point, but for now, just to keep it simple, I didn't. But if I tell my Vectrex emulator to load symbols from this map file, then when we run it, we should see some nice symbols. I'll have to take a look at your thing, maybe just a bit later if you don't mind. Okay. So what was I doing here? Oh yeah, that's it. So let me go to my debugger. What I wanted to show you was the call that is being made here. Oh, did it not? Loaded symbols for, no, that did work. Where is my C100? Did I have to build in debug? I might have had to build in debug. Let's see here. C100. Okay, so I think I'm missing. Or maybe I don't have those symbols. Now that I think about it, why would I not have those symbols in here? These are the functions. Yeah, it looks like I don't have symbols in my map file for globals. All right, doesn't matter. It's fine. Something to look at later. So what I want to show is here you can see, I think it's C100, right? So if we go back to Vectrexy, so this header, by the way, I called it vectrexy.h because this is very specific to Vectrexy. Anything that's Vectrexy specific will go in here. So there, C100. So that's what we write to when we want to write like a 1 byte value. So you can see here we're writing 1 and then we're writing 0 here, and I don't even remember what we're going to print here. Let's just see what happens if I remove this. So I just keep stepping and boom, there we go. So you see score 1, 1, score 2, 0. So that 1 and that 0 that we were writing here, that's the score value itself. So those are the 2 arguments for the printf call. And then I think the final call here is this here, 05DA. We load X and I don't even see what the right is here. I guess it's this one here, C105. Yeah, it's just weird because it's just because my debugger is outputting after the debugger is outputting that line, you know, after, or I should say, the trace here is coming from the dev memory device before the debugger gets a chance to output, which is why it looks a bit weird in terms of the order. But basically, we're storing the value of X. So we loaded the value of X with the format string. So this here is where the format string is in memory. We can actually see it here with the debugger. So if I take this address, 05DA, and do a print of my address, it's true, I don't print the ASCII value, but let's say I do A, B, C, just to get a few. And basically I've got 73, 63, and 6F are the hex values, which are I suck, not very good at ASCII, but let's just look at the ASCII table. So 73, right? What's 73? So 73 is I? Oh, that doesn't make sense. 63. Oh no, sorry, hex. Yeah, hex 73. So hex 73 is here. So it is the letter S. So that's right, because I'm outputting score. So you see, like, we go look at the main here. So that the first, so it should be SCO. Those are the first 3 that we're looking at, right? So I'll come back here. So we've got S for 73. 63 hex is C, and then the next one should be O. So 6F. So 6F is here. 6F is O. There we go. So you can see basically that that is indeed what it's doing. It's just writing that out. And if you think about it, like, this code here is really, really cheap, right? In terms of cycles, like the whole printf from the point of view of the Vectrex is just, you know, in fact, we can even calculate how much, you know, cycles it is because we output the cycles here. But, you know, we load a value, we store it. We load it, we store it. We load it, we store it, you know? And so it's about, let's see, for that one printf call, we're looking at 18 cycles. Oh no, sorry, including this one. So say 23 cycles. Not bad, right? If I had to write, you know, a proper printf that runs on the Vectrex itself, it would take hundreds of cycles, you know? So anyway, I thought that was kind of neat. Just wanted to share that. So I don't think I'm going to actually have a lot of time to program tonight. This is sort of my, like, let's get back into it and reintroduce what I've been working on. But I did want to talk about what it is that I'm working towards in Vectrexy now, like my next goal. And what it is that I really would like to be able to do source level debugging of, you know, my Vectrex game that I'm writing here. Oh, hey, thanks for the follow, man. Really appreciate it. Too many JS programmers. So, yeah, so what I really like what I think would be so cool would be, you know, I'm here and I'm writing my C++ code for Vectrex, and I want to put a breakpoint, you know, right here and hit F5 or whatever and start debugging and actually be able to debug. So, you know, how can I do that, right? And where did I get this idea from? So this is not a novel idea. This comes from a few years ago when I was doing some Nintendo DS development, homebrew development. And at the time, I was using this emulator called, I don't even know how to say it out loud, Desmume, Desmume. The emulator that's unpronounceable. Anyway, this guy here, this emulator, it's a very good DS emulator, but this emulator has this feature which is called the GDB stub. If you look up Desmume GDB stub, there's people asking if anyone uses it, but basically it's like a way to the emulator runs, and it runs some code that can talk to a GDB remotely. And then what you do is you compile your C++ programmer for DS using the tool chain, and it produces an ELF with, and if you tell it to, if you pass -G to GCC, it'll add debug info, so dwarf info into the ELF. GDB loads that up, it sees the debug information, and you tell it, connect yourself to this socket. And Desmume is listening on this socket and runs this GDB stub to talk to GDB. And it's a text-based protocol. You've got a lot to say. I hope it's interesting. So this is super cool. I thought this was such a neat feature. And I actually, in fact, I don't remember where it is, but I even wrote a blog post about it. GDB Nintendo DS. Let me see if I can find it. Here it is. See, back in 2011. So back in 2011, I wrote this blog post on my very old Blogspot blog. And it's like how to debug your NDS ROM using the Visual Studio Debugger. And, I sort of go through there and show the C flags you want to set. And at the time I was using this extension for Visual Studio called WinGDB. This would be completely unnecessary today because Visual Studio has its own free GDB extension. But yeah, you see you have to tell it how to connect, and this is basically the GDB command. You say remote localhost and you give it a port. That's the one I think Desmume listens on, or you tell it. See, you run the emulator this way. They have like a dev version of the emulator, and you tell it, for the ARM9 chip, I want to have it do the GDB thing on port 20,000. And then you run it with your Nintendo DS image here, which is really an ELF, and it starts listening for commands, and then GDB starts talking to it. And sure enough, I didn't take screenshots here, but sure enough, you end up being able to set breakpoints and step and all that. And I thought, so cool, I want this to do the same thing. And so I started actually writing a GDB stub and got pretty far. See, I have here a work in progress branch, and you can see that there's quite a bit of code here that I wrote along the lines of implementing a GDB stub. But I should have done this, I should have checked before writing all that code, but I was like, I just assumed that since I was compiling with this fork of GCC, GCC 6809, that it would be able to produce the ELF with the dwarf symbols that I need. Unfortunately, it does not. You see, GCC 6809 produces a different data format, which is apparently known to people who work in embedded. It's the, I think it's S19. Is this the one? I think it's this one. Or no, I don't have the output here. Let me see here. Give me a sec. It's in the make file. So the file format that I'm thinking about is the S19. And it's kind of like this format. It's a text file, but it's got in it basically binary values. And the idea is that you sort of sound it, you build and then you send this directly, let's say, over a wire to an embedded device. And it's just like it copies byte per byte into some RAM chip or ROM chip, and that's that, Oh, sorry, said who. I I mean, I hope it's somewhat understandable. So, okay, so all of this to say is that I'm like, oh, you know, there is no elf, there is no dwarf, and that's what GDB wants, right? GDB is looking for this information. Yeah, so I am trying to debug games. So like what I would like is to run Vectrexy and then have it, you know, like connect and listen on a socket, and then, you know, use GDB to load up the binary of my game and have it connect to my emulator so that my emulator can respond to, you know, where is the what instruction is the CPU at right now? What are the values in memory right now? Because that's what GDB needs in order to provide you a source level debugger. You know, the ability to be able to step through your source and look at values in your, you know, the values of a variable. All of that is doable when your debugger can know, you know, where is the program counter right now? What's the stack look like? You know, what's the, you know, where it wants to know basically everything about your program, right? It does it at the binary level. Yeah, pretty much, right? So, you know, when you're debugging a program like the kernel, let's say on Windows or Linux, the kernel is basically answering all those questions for the debugger. But if you're working with an embedded device, let's say external, you need something to talk to the external device. Sometimes it will be like, you know, another chip on your embedded device that implements this protocol. Sometimes it can just be, you know, some piece of like a daemon running on your host that is translating between the device and GDB. So that's where the GDB stub comes in. Having said all that, I spent like a week looking at, can I get this debug information? Can I maybe build an elf? You know, can I create an elf and inject dwarf symbols? Should I maybe modify this GCC 6809 fork of GCC to output the elf with the dwarf symbols just so that I can debug? And I thought, wow, this is really going to be a lot of work. I don't really want to play around with that fork of GCC. GCC. It's just, that just doesn't sound interesting to me. So instead, there is something that I can do, and this is what I'm hoping to be able to do. There's this protocol that Microsoft defined called the Debug Adapter Protocol. So here it is. So DAP for short. So the Debug Adapter Protocol is a protocol. It's open source. It's a specification that details a generic debugging protocol. And the idea is that, you know, one person, or in fact, I think they have a really nice image here. So here they describe like the typical system that, you know, we've gotten used to. So you've got a whole bunch of development tools, IDEs, editors, other tools, and then you've got debuggers, right? And each one of these applications has to know how to talk to that specific debugger. So like GDB, the debugger for, you know, C#, or the debugger for Python. And you can see that, like, you know, if your IDE supports Node.js debugging in Python, it needs to actually know how to talk to the Node.js debugger for Node and the Python debugger for Python. And if it supports other languages, it's got to have, you know, support for each one of those. And obviously this is the state of affairs actually right now, or has been for years, and it doesn't scale very well. It's you know, we end up with subpar experiences, or like, oh, I like to use this IDE for this one language because it supports it really well, but I use a different IDE or a different editor to debug this other language because it supports that one really well. You know what I mean? So what they decided to do is to introduce this layer called the Debug Adapter Protocol in between. And what happens here is that all your tooling, your IDE, your editor, your tool, just need to implement this kind of generic debugger that talks to DAP to this protocol, to this adapter. And then DAP is written to know how to, like, or an adapter is written per language, right? So there's an adapter for Node, an adapter for Python, an adapter for C# that adapts this like higher level generic debugging commands to the specific ones for each language, right? And then these here talk directly to the debugger. So it introduces this layer in between, which is really cool, right? So it's very, as they say here, it's very similar to the approach that Microsoft took with the language server protocol, which has become quite popular. I think Vim implements it, and a bunch of other editors, obviously VS Code, where you have the language server protocol is the one that allows you to do things like look up where functions are defined or used, and syntax highlighting, stuff like that, right? So they want to do the same thing, but for debuggers. So all that to say is I thought, well, why don't I do this? Why don't I implement a debug adapter protocol for the Vectrex? So it's like an interface. Yeah, exactly. You can think of it as an interface. Yeah, it's an API. It's an API, and providing. Oh, hey, thanks int45h. Thanks for the follow. So yeah, it basically provides this API that allows things to talk to debuggers. Oh, cool. Well, welcome to the stream. So so my idea would be that I would use, in my case, I'll use VS Code, but anything that supports DAP should work. And I will write a adapter protocol for the Vectrex, and it will basically it's going to be hosted within my Vectrex emulator. So it won't be like a separate, here they show us separate boxes, because that's actually how it's often done. There's a separate process here that will talk to the Python debugger. But in my case, it'll be like one box. It'll be Vectrexy, and in Vectrexy, I will have a debug adapter protocol implementation. And for that, since it's in C++, I'm going to be using this thing called CPP DAP. This is actually implemented by a colleague of mine. So he, someone I work with, he basically wrote this really cool, really nice library to make it much easier to implement the protocol in C++. Otherwise, I'd have to do all the socket stuff and the threading stuff myself, but he made it really, really easy to do that with this library. So I'll be looking at this, to give a simple. He has a nice little example here that sort of shows a little bit, and I'm not going to go through it, but he writes a really simple debugger, and then you can see how easy it is. It kind of the magic starts here, where you create a session and you start setting up all the debugger events. So like the debugger will you'll get an event for the stepped or breakpoint hit or paused. You'll register things like when an error occurs, register handlers here. So I think this one here is for, these are first, okay, so the API, the protocol, has a bunch of messages you need to respond to. So there's one called initialize request. Why is debugger in red? Where do we see debugger in red? Sorry. Oh, here. You're asking why the color is red? I don't know. I think that's GitHub doing some syntax coloring. I think it's a type. I don't know. Yeah, I think so. I think you can see this blue here for functions and stuff. Yeah, it's GitHub. It does some light syntax highlighting. So anyway, like there are a bunch of messages that you have to respond to that the debug adapter protocol specifies. So VS Code is going to send an initialize request, and you want to respond to it. And you can see how easy it is with CPP DAP. You just say, when I receive this, create a response object and start setting values on it, and then just return it. And it's going to take care of actually packaging this up in the format that's required and sending it back. So yeah. And there's also like other messages that you've got to handle. So yeah, my plan is to do this, implement something like this, and hook it all up to my own debugger so that I can do all the stuff that's needed to be able to do source level debugging in C++. So that's it. I'm kind of excited about working on this. I don't know where it'll take me. I hope it works well. I think it'll be fun. You know, maybe it won't work super well. Maybe I'll have some issues, but I think it'll be a really fun journey and kind of interesting thing to do. And I think also if it works out well, it could be an inspiration for other emulator authors out there to look at a different option for writing debuggers, because everyone sort of writes their own custom debugger, just like I did, right? Like here, this is my custom debugger. You know, it looks a lot like GDB, allows you to do stuff in there, but like, and that's cool, and I highly recommend that you write your own debugger, but ultimately it's a lot of work. Everyone's sort of repeating this work, and if it's possible to compile C or C++ for the target, and there is a tool chain for it, well, you know, DAP would be an interesting way to write a product, to allow for tools to be able to talk to it. You know, sure, if the tool chain is GCC based and can produce ELF with Dwarf, you can go for the GDB stub. But actually, I find the GDB stub a little bit annoying to implement. It's very old and text based and finicky to write for, and also you need your tooling to support GDB stub or to support GDB. And although most IDEs and tools do support it, you know, and probably more actually than DAP. Like I said, it's a little bit old and a little bit limited. So one thing about DAP is that it's, you know, GDB is great, but it's sort of for Linux. You know, Microsoft has made a lot of headway into supporting GDB stuff and GCC, but you can't like debug a native Windows application with it, for instance, right? So yeah, all that to say is that DAP's a little bit more abstract, it's more modern, and I think probably easier to implement. So this could be interesting for other authors, emulator authors. Let me catch up on chat here. So can you give me a link on DAP explanation? So I think you mean this one here. I could post that in here. Int45H, sorry for the dumb question. Don't worry, there are no dumb questions. But when writing a dynamic compiler, do you have to be familiar with traditional compiler design, generating ASTs and stuff, or can you just jump right in? So I assume you mean JIT, right? Like you're talking about for your emulator, if you want to create you want to JIT some stuff. Is that what you're talking about here when you say dynamic compiler? Yeah. Well, I mean, I don't think you really need to know how to write a traditional compiler. JIT is more like learn the API available. You are, in effect, building an AST when you're using a JIT API, but for the most part, it's sort of taken care of for you. So I think it's possible to do it without really knowing how compilers fully work. You know what I mean? You do need to. I think you need to know more about, like, maybe I'm wrong. I guess familiarity with ASTs is good. You know what I mean? Just understanding how to read an AST or what an AST looks like for a program could be valuable. A lot of tools out there to help you with that. A lot of Clang-based tools can help you learn that. But yeah. Yeah, we might do this. Oh yeah, for sure. Ness might benefit from this. There's a very primitive C compiler for it. All right. Yeah, so I don't know if that compiler would produce ELF with debug symbols, but if it doesn't, this could be a good option. Or in either case, it could be a good option. I do think, like, I will say, there in terms of the amount of work I would need to do to support this protocol, I think there is more work implementing DAP than there would have been for GDB. I think, just from what I've seen between the two. I think that GDB is a slightly lower level, so it can do things like just, you know, it implements a few, it needs less from you. It's fine with being able to read from arbitrary addresses. If you can give it access to your memory, it can figure out a lot of stuff for you. So a lot of the onus is put onto GDB. Whereas I think with DAP, they sort of put the onus on the adapter itself. So they've kind of put a little bit more, it's a bit higher level. It's saying, you know, rather than, let's say, as an example, GDB, I don't think necessarily needs call stack information. It can sort of figure that out based on a few lower level calls, whereas DAP says, hey, give me the call stack. You know what I mean? I might be wrong on that, but something like that. So DAP's a little bit higher level, so it's a bit lighter for the editor to be able to deal with, and puts a little bit more work on the adapter implementer, which I think is fine, and I think it's fair even. It would make more sense that way, right? Because we want more of these guys to use DAP. So you want to make it simpler for these people and put the harder work in here, because this will be reused by multiple people. You know what I mean? So yeah, I think that's it. So before I end my stream, since you guys are here and you don't really know the Vectrex here, I'm not showcasing the best game for the Vectrex, because this is just my sample Pong game. But I guess I could show you guys a couple of Vectrex games if you're interested. So let's see, where are my... Okay, so let's see. So here's an example of a game that makes use of the overlay pretty well. So you see like the overlay here. This is like a tank game. You're a Jeep or something, or a tank. I don't know what. These are tanks coming out, and I think you're a Jeep that shoots missiles. And you can see that the overlay sort of tried to draw this kind of war field. You know what I mean? And then they drew lines around them. So, and basically you. And there's a helicopter that's going to come. I find the helicopter kind of neat. Yeah, the sound chip's pretty neat. So that's Armor Attack. There's this game Berserk, which is pretty well known. Okay, this sound is totally messed up there. Trying to fast forward there. So Clean Sweep is kind of like a it's kind of like a Pac-Man clone. And basically, you're like a what do you call it? A vacuum. So once you fill up, like this is like kind of like dust particles, and once you fill up, you keep getting bigger and bigger, and you also get slower and slower as you get bigger. So that's Clean Sweep. Pretty cool game, I think, is pole position. This one here. Okay, I think. Let me see I haven't played this one in a while. So I think it's pretty cool, right? Like this is where you can see how vector graphics can be pretty nice, you know? The curves are really cool, like, as you point out. And also the scaling, you know, like if you play racing games on a regular raster-based system, the cars that come in don't typically scale very well. They sort of have different sprites that they sort of pop to, but here they actually scale really smoothly because you can do scaling with the vectors, you know. So that's pretty neat. And then you crash. What else can I show that's kind of neat? So there's a lot of homebrew, actually. Yeah, there's a lot of homebrew for that's been done. I don't have them all here, but I have a few. Let's see, which one should I show? So this guy, John Donzilla, I think he's sort of the guy responsible for starting the homebrew scene. You like the Pong one? Well, thanks. So this guy, he's sort of prolific in his games. You can see he really kind of got how to take advantage of the hardware here. Yeah, he's pretty awesome. I think he even made this overlay and stuff. So like, it's basically a bunch of games. Press button 1 to play. You can kind of change between different games. You've got like Rockeroids, More Invaders, Vectress, and Spike's water balloon. Spike is sort of like the mascot for the Vectrex. So like, let's say we do this Vectrex here, Vectress. It's a Tetris game. And actually, one thing you can see that my emulator does not get these blocks to render completely straight. So there's still a little bit of tweaking I got to do there, you know? So yeah, basically stuff like that. So that's my little showcasing of what the Vectrex can do. So yeah, I think I'm gonna end it here because I don't think I'm gonna start on this. This is sort of my, like I said, coming back. Hopefully next week on Tuesday I'll be able to stream again, and then maybe again on Thursday. So I am trying to get back, and I won't make promises. But my voice actually is running out. I'm out of water, so I'm gonna stop it here. So yeah, thanks for watching, guys, and yeah, hopefully I'll see you next time.